Hello everyone, welcome to my channel. This is Ready Tuma. Today I'll be presenting you out a machine learning project, which will probably be very interesting. And I come up with a project of hard rate prediction using machine learning, where we'll be using many machine learning algorithms. The motto of this project, why I started this, is because roofs are leading one of the death causes, and they are really disrupting the whole world. So the sad truth is about many of them are preventable with early detection. Now, what I thought is about using machine learning isn't just an innovation. So it can actually save many people lives also. So I came up with this project, and now to start off with the project, first I've initially imported all the libraries such as Pandas, NumPy, Matplotlib, Seaborn, and also all the Scikit-learn. Now, initially, I'm just currently taking out my data set. Now, initially, I just firstly printed out all the top five rows in my data set. And now, you can see the features over here like ID, gender, age, the hypertension, heart diseases, if he's married or not, the word type of that person, the residence, the average glucose level, the body mass index, uh, smoking status, and the outcome is if that person has stroke or not. So to start off with, you can see the description about the data set. There are, you can see the data type also. ID is an integer, gender is an object, age is a float number, hypertension is an integer. You can see the description about which data type do they belong to also. Now to find data pre-processing technique is actually very important because in order to make sure that uh, the models perform really better, we need to provide a correct set of input to the models. And if we provide any kind of noise data, what do you mean by noise data is any kind of outliers or any kind of missing values over here, like that in the data set, the models do not perform better. So, in order to clean the data or to extract meaningful information from the data, we'll be performing some data pre-processing techniques. So, as you can see over here, the first one is we are initially calculating the null values in our data set. So, as you can see over here, the body mass index has 201 null values. So what we'll be doing over here in this particular set of code is we're actually calculating how many missing values were there and the kind of percentage, and we're just displaying it out here. So generally, machine learning models really work better with numerical values rather than categorical values. Why? Because machine learning models are mostly mathematical models. They are basically built based on linear algebra and calculus. So they understand more numerical features better. So in order to convert, we have different categorical values in our data set like gender, if he's married or not, the residence type, like urban or rural area, and the smoking status, if he just smokes or not. So what I'll be doing over here is I'll be converting each of these things into numerical values by using a label encoder. And after transforming them, you can see the output over here. Now, similarly, we initially found there are a lot of missing values, a lot of null values, sorry, in the body mass index. There are totally 201 missing values. So what we have done over here in this particular code, snippet of code is we are filling out each of the values of the null values with the mean of the body mass index. Now, after finding out this stuff, you can see the body mass index has no null values. Now we are just displaying out the top five elements over here, and similar is the instance over here. If there are any dummy values, we are trying to remove that as well because it will try to increase the time complexity. It doesn't give any much sort of sense over here. Initially, as you can see over here, in this particular set of code, they're dropping the ID. ID is just like a unique number that can be given to a person for identification. It doesn't make any much impact for improving our accuracies, the performance of the model. So we are simply dropping it out here. Um, since in our data set, if we find the actual value, that is, if the person has stroke or not, um, we can see that the person doesn't have stroke are totally 4,861, and the person who has stroke are just 249. So no has the no is the majority class over here, which will be affecting the outcome. It is completely biased. So in order to balance this thing, we are using a technique called as SMOTE over here. First, how does SMOTE really work? SMOTE stands for synthetic minority. SMOTE stands for synthetic minority oversampling technique. It is a popular machine learning technique where we'll be addressing the problem of imbalanced data sets, especially in classification tasks, like if a person has stroke or not, similar to our hash rate prediction one. Here, what we'll be doing over here is it will mainly focus upon the minority class over here. For each minority class, Smoot will find out the k nearest neighbors within the same class. It will be generating some auxiliary data points within the specified range of the data set, and it will be balancing out the minority classes with the majority of the classes. So, as you can see over here, after balancing out these things, um, we've actually balanced out here. You can see here the number of yes and the number of no are equal. So we've balanced the data set over here, and similar is the graphical representation over here. And this is all about the data set exclusion. And as you can see, correlation is nothing but how one feature in the data set is related to another one. So here initially we're trying to find out the correlation of each feature with respect to stroke, and these are the values have their dependent. You can see the values. If the correlation is one, they are positively correlated. If the correlation is negative, that means they are negatively correlated. That means if one increases, the other one decreases. And if the correlation is zero, that means they are not related to each other. So here you can see the correlation matrix over here. Each feature is positively correlated to itself. So that's why you can see all of these diagonals as one. And this is how exactly it is. And we're trying to represent these things in a pictorial way, in a graphical way, so that we can get the more intuition from the data set. You can see gender, zero means it is female and one means it is male. Similarly, for hypertension, if the person has hypertension or if the person doesn't have any hypertension. So similarly, you can see if the person is married, the number of persons are almost 1,800, and the number of persons who are married is greater than 3,000. So this is the basic intuition of the graphics of the graphs over here. Now, since our data set doesn't really consist of exact within some specified range, there will be some numbers which are out of box. So these out of box numbers are called as outliers. So this will probably, when we pick any kind of a model for the data set, these outliers ensure that the model doesn't learn the patterns pretty well. So what we'll be doing over here is we'll be calculating the 25th and the 75th percentile, and you can see the number of outliers over here for each feature. For hypertension, there are totally 498. For heart disease, there are 276 outliers. And for average glucose level, there are totally 627 outliers present. So what we'll be doing over here is we have initially um, the ones which are greater than 95th percentile are mapped as a 95th percentile, and the ones which are less than fifth percentile, which stays between 0 to fifth percentile, are mapped as fifth until fifth percentile. Here we did not drop any outliers because sometimes outliers can also give uh, an interesting pattern for the model to learn. So that's why we didn't drop the outliers. We initially just scale them and we just map them over here. So after doing all that stuff, um, you can see over here. Now, after doing all of these pre-processing techniques, we have initially found the null values replaced with the mean values. We initially used mode in order to handle the imbalanced data set and later balancing them. And later, we also performed outlier, reduced the outliers. We brought them to certain values. And now, after doing all of these data pre-processing techniques, now we are trying to fit these things into our model. So here we will be uh, importing our model from Scikit-learn, and from here we'll be dividing the data set into two parts. One is the test data, and the other one is training data. So for test data, we are actually given 20% of the data set. For training data, we are given 80% of the data set. So you can see over here, we are actually applying five different algorithms. Uh, they are KNN, logistic regression, decision tree, uh, random forest, and XGBoost. So for each of these models, we'll be fitting these models, and then we'll be finding out the accuracies over here. So we are initially fitting out KNN. We gave the K value to be as 3. And then after putting that into the model, you can see the accuracies are 90%, the precision is 85%. Similarly, when you find even with decision tree, similarly is the case. We're just fitting out the model by using dot fit method. We're just putting out that instance using SQL, and then we are just fitting out the model and just trying to find out the accuracies. We gave 91% accuracy and a precision of 89.7. And similarly, we gave navy bias also, navy bias and logistic regression and XGBoost. So these are some of the things that we have done, and also last but not the least, we have also applied random forest classifier. So it sometimes we cannot get the most important features. So for a model to learn the patterns, interesting patterns, and thereby predict the output pretty well, it really requires some important features. So here is where we made the project a bit interesting. We've initially passed the data, we've removed the low variance filters. What do we mean by variance? Variance is the how spread the data is. For example, what do we mean by low variance? In the project, we used low variance technique. Uh, Low variance means the data points are scattered around some particular region. That means they're not scattered throughout the whole graph. That means it doesn't give much information. If the data is scattered throughout the whole graph, only we'll be getting to know how well our data set is, it will give the interesting patterns. If the data points are present within some particular area, it doesn't give any much information. So low variance means it doesn't give much information. High variance means it gives more information. So what we are trying to do over here in the code is uh, first we'll be passing out a variance threshold. If the values are below that threshold, which means a low variance, we'll be simply removing them. The output of this low variance is passed as an input for PCA. Now, what does PCA mean? PCA stands for Principal Component Analysis. It is a dimensionality reduction technique where we'll be getting out the most important features and will be eliminating the redundant ones basically. So, how does PCA give the most important features is um, it helps in maximizing the variance. As I already mentioned before, variance is nothing but how well the data is spread across, right? So, if the data is spread across in a much wider way, it gives more information. So that is what PCA exactly does. It captures the features which gives more information. That is where our model really tries to learn the more interesting patterns. So, as I've just said earlier a bit, just now, we're just setting out a threshold over here. After setting out the threshold, we're just removing them. The features removed, we'll be displaying them over here as well. And after doing so, we'll be applying the principal component analysis. And these principal component analysis will vary a bit based on n components, where stands the top n features. It can be any numeric value. So we are just currently passing the output of the row variance filter to the input of PCA. And the output of PCA will be the most important features, which signifies that it has maximum variance. So this is the implementation of how PCA has been working. Um, you can see this, how well this is placed at the moment. So you can see the initial data set is 9,722, and there are totally 12 features with uh, excluding the output feature that is stored, if the person has stored or not. So after removing the low variance filter, everything satisfied the low variance filter. So that's why you can see original features are 13 and features retained are 30. That means no features are removed. Now, after applying PCA, which has we've set it to 95%. So the PCA transforms this 13 features into 11 features basically right now. So our n value can vary. So as you can see over here, this is the heat map, how one PC is contributing uh, to maximize the variance over here. We can apply this PCA with n different components. We have applied with 5, with n components equal to 5, n components equal to 7, n components equal to 9, and n components equal to 11. Now, after performing out these things, we have compared um, the model's performance before applying the hybrid feature selection technique, and after applying the hybrid feature selection technique. So we observed the accuracies, the performance of the models was increased after applying this hybrid feature selection technique. Uh, just because PCA gives the most important features, that's why it helps in increasing the performance of the models by just eliminating the normal features, uh, which doesn't have much impact on the outcome. So as you can see over here, for n components of PCA of 11, RKNN gave 89% accuracy, Logistic gave 82%, HC Boost gave 90%, Random Forest has shown 92% accuracy. So these things will definitely vary a bit with respect to n components. So out of all of these components, this is the same code that we've been applying before. The one we've applied for n components equal to 11, and now we'll be applying for n components equal to 9. So on, we'll be applying for n components equal to 7 and n components equal to 5. So simply as you can see over here, uh, you can see the features which were even removed over here. So these shows the features, the actual features, and these shows the features which were currently removed. So after finding out these things, the model which gave the highest accuracy is random forest. Now, let me just tell you why it gave maximum the analysis, why it gave more amount of stuff like that. Random, we all know that random forest is a collection of decision trees. The disadvantage with decision tree is it is prone to overfitting. So, in order to overcome that disadvantage, we'll be performing a boosting technique, which is nothing but random forest, which is nothing but a collection of decision trees. So, after we'll be initially dividing the data set into different subsets, and each of these different subsets are passed to the decision classifier. And after performing out these things, we'll be doing either majority or average voting, and then we'll be predicting the outcome. So, since it removes the disadvantage of the overfitting of decision tree, random forest, which is boosting technique, which will try to improve the model performance. It gave the highest accuracy as 96 percentage. And the next one, which gave the highest accuracy, is XGBoost. It is nothing but extreme gradient boosting. It is a powerful and widely used machine learning algorithm. Uh, it is a type of gradient boosting algorithm. So this is also an ensemble learning method which is based on decision tree again. It builds sequence of decision trees where each tree will try to correct the errors from the previous ones. So that's why it gave the next highest accuracy over here. Now you can see over here. Let me take you through this code. I mean for encombrance, be it 5, 7, 9, or 11. The code is same, just the encombrance keeps changing over here. As you can see over here, in this particular set of the hybrid feature selection technique, first, initially, we are doing standardization to scale the data. That means we are bringing out the mean to zero and standard deviation to one because it is essential for many machine learning algorithms. Later, as I said before earlier, we apply low variance filter. We set the low variance filter to be 0.01%, which is nothing but 1%. The ones which are less than 1% will be removed off, and the ones which are greater than or equal to 1% will be staying in the contest. Later, we'll be applying the principal component analysis. Um, which shows the maximum variance of 95 percentage. And later, we'll be doing a lot of visualization techniques. Over here, we have drawn different types of data visualization techniques. We have drawn how one feature is related to the other feature, and the top K features over here, and also the top K features that are selected by lasso. And we have also shown the accuracy F and score comparison. And also you can see over here the performance matrices of across all of these models. So based on this, before applying PCA, the model showed around 90 to 88 to 90% or 92% accuracy. After applying these hybrid feature selection techniques, the model has shown almost around 94 to 96% accuracy, out of which random forest has shown the highest percentage of 96.2 percentage. So this shows by applying PCA, it will reduce the time complexity by just focusing upon the main components. Um, Now you made it out that there are different components of 5, 7, 9, and 11. So how will it vary? So for example, at some PCA equal to 5, then value equal to 5, the graph slowly keeps increasing forward. That means that the performance is increasing. At 7, the value is still increasing. At 9, the value has reached the highest. That means the 96 percentage which I've said before. So after 9, now if I take n equal to 11, initially we just had 13 features, right? Now, if I'm taking 11 features, which is nothing but I'm assuming just two features, it is trying to take almost all the features apart from those two features. So it doesn't, sometimes it may reduce the accuracy. So at PCA end component equal to 9, the accuracy is highest. After that end components where the performance of the models is reducing, that particular region of where end components has reached the highest accuracy or highest performance of the models is known as trade-off. After reaching some value of n, the highest value of uh, model's performance, and thereafter the model's performance keep decreasing, and that particular term is called as uh, is generally known as trade-off. So this is what my project is all about. Um, I hope you guys have done that pretty well, and I hope you could do something from this and ensure that you can. So thank you so much, and here is what I'll do. So thank you.